Okay, welcome everybody to Solar Noon Tuesday. All right, we're going to start out as per usual to talk about some of the solar news of the week for the week of February 20th. So in the legislative front, there are a couple of states out there that are doing some activity within the renewable energy sphere. Maryland legislature has a bill before it that's going to boost. They currently have $1,000 grant for residential homeowner to pay for some of the cost of installing solar. They're looking to boost that to $5,000. So it's a grant subsidy for installing solar on your home. The state has some renewable energy goals. They're looking to reduce greenhouse gas emissions by 60% by 2032, and they have a net zero of by 2040. So the way that they're going to be paying for these grants is any of the companies that don't meet these goals are subject to fines and penalties. So they're going to be using these fines to subsidize the installation of solar on homeowners. So we'll see where that goes. New Jersey Governor Phil Murphy announced on February 14th at Rutgers that their 100% clean energy goal for the state is going to be moved up. Originally, this goal was by 2050. Now they're moving up this goal to 2035. And they're also announcing that they're giving grants, state grants for electric vehicle transition, and that they have set the policy that by 2035, 100% of the vehicles sold within the state of New Jersey will be zero emission vehicles, essentially electric vehicles at this point. The same type legislation already exists in California. This project, dubbed Project Nexus, is being put together by a company called Solar Aquagrid, and it is the first solar over canals large-scale grid-tied project that's announced here in the U.S. It's going to incorporate batteries plus solar in Central California. Now, the University of California did a study that showed that there are essentially 4,000 miles of canals in the state of California, and that these canals could house 16 gigawatts of solar power, which is about 1/6 of the current installed base of solar within that state. Not only will these solar panels over the canals generate electricity, and actually the cooling nature of the canal should increase the efficiency of the system, but it's also looked at for preventing or inhibiting some of the evaporation or the water loss due to evaporation. In fact, that study by the University of California estimated that about 63 billion gallons of water would be saved each year, which is enough water to service about 2 million people within that state. And additionally, it's nice that these things would be installed on areas that aren't really being used for anything else other than water going underneath, as opposed to farmland, which is always going to be in short supply. McDonald's has announced that they're going to be buying power, all of the power that's being generated from a new 180 megawatt solar array in Louisiana. Now, McDonald's has announced that they're looking to go to net zero by 2050. This particular development will provide enough power to service about 630 of their restaurants. And this is a trend that we're seeing in a lot of commercial enterprises. But the thing that was interesting with McDonald's is that in December last year, they announced that they're beginning to aggregate some of their power purchase agreements and bringing in some of their small suppliers, so that a supplier who is servicing McDonald's, who otherwise couldn't afford or qualify for a power purchase agreement, is being brought in under that umbrella. So they're kind of sharing the wealth there in that other people, other businesses can get involved in some affordable and high quality power purchase agreements under the umbrella of McDonald's. That may be a trend that we'll begin to see from other large corporations as well. And Tesla announced they're going to begin opening up their charging station network to non-Tesla vehicles. Prior to this, it's only been Tesla that could use these EV charging stations. They're estimating they'll have about 7,500 of these available by the end of 2024. And this is part of a process. We've talked about this in previous sessions of an expansion of the electric vehicle charging infrastructure. Hertz and BP, Hertz, the car rental agency, have announced that they're going to be building a network of fast charging stations. In fact, BP is going to be investing about $1 billion in this process. And Hertz, for their end, they're looking at transitioning a quarter of their rental car fleet to electric vehicles by the end of next year, by the end of 2024, which is quite rapid. And as part of this agreement that they're doing between BP and Hertz, they're not only going to put charging stations at the Hertz rental car outlets, but they're also looking at creating what they're calling giga hubs, large EV charging stations located in those places that have high charging demand, such as airports, along interstate highways, places where taxis might congregate. In fact, they're really looking at not only servicing the rental car marketplace, but also the ride sharing and taxi industry. Some of the studies out there have shown that, for instance, companies like Uber, they only represent about 2.5% of all of the vehicles that are out there on the road, but they do represent about 30% of all of the fast charging that's taking place. So disproportionate. So what they're wanting to do is target that marketplace. And in another EV charging thing, the General Motors has announced that they're going to start installing about 40,000 level 2 charging stations in communities across the country. And the level 2 are those 240 volt stations that you might install, for instance, in your own home. They're trying to pave the way where there's access to quite a lot of charging stations as all of these vehicle companies begin to transition to EVs. And in the final bit of news that I found this week, even in the state of Texas, I shouldn't make fun of Texas, but Texas poll by the University of Houston has found there is a large support for the transition to renewable energy within the state of Texas. I think most people outside of Texas may think of it as a more fossil fuel oriented state, but 64% of those people polled said they approve of the transition to solar, 59% approved of the transition to geothermal, 57% to wind, while only about 41% of those polled said maintaining nuclear and natural gas energy or electric sources was a good thing. 90% of those polled said they support an aggressive net metering, where the net metering is paying retail for what is generated back to the grid. And 82% of those polled found, they stated that they approve of government subsidies or incentives to people to install solar. So that was the news from the solar industry for this week. So anybody have any comments on the news or anything to add on that? Give you just a second. Well, everybody's being quiet. All right, so you can just jump in at any point, and I'm used to being interrupted. So the item that I thought I would bring up as sort of our focus point here this week is I did get a question, and I've had these questions before, where they're talking about checking or verifying output from your solar array as opposed to the nameplate rating. So let me try and further define what I'm talking about here. So we often refer to these solar arrays like that's a 5,000 watt or a 5 kW array or a 10 kW array, whatever the size of the system may be. And for those of us who are out there installing PV systems, we understand what that means. Basically means that under standard test conditions, that solar array will be producing that much power at the DC power, okay, not necessarily the AC power. So so if we have, for instance, a 5,000 watt array, then the customer will have the expectation in their mind that that thing's going to be producing 5,000 watts. So that when they look at the system, it should be producing 5,000 watts. They're not going to be sophisticated enough to know that temperature will affect it, irradiance will affect it. You know, there's a lot of things that are going to be affecting just how much power that outputs. They're going to say to you, listen, you told me this was a 5 kW array. I'm looking at the output from the inverter. It's a little thing right here on my phone or right there on the inverter, and it's not saying it's producing 5,000 watts. You screwed up. You know, something's wrong with this system. So I'm going to walk through the example. Now, I can't help you convince your customer that everything's working perfectly, but you should at least be able to, for yourself, understand, is the system working the way it's supposed to at the time of commissioning. Typically, this is when you would do this kind of evaluation. So we've got, in this example that I'm going to walk through, we've got a little array. It's a 5 kW array, just a basic string inverter. But let's say, for example, that we look at the AC output from the inverter at the time of commissioning, and we find it is producing 3,750 watts. So the question is this system producing as it should? And I'll give you a little advanced hint that, because I did the math, yes, it is. But this is just something that I wanted to walk through. So how do we figure this out? Well, the first thing you need to do is to get the panel specifications for the panels, the service panels that you just installed. The service panels, no, the solar panels that you just installed. So in this example, using Canadian Solar 250 watt solar panels. So if you look there in the circled area, the 250 watt panels, they're going to have a VMP of, my vision's not that great, it's far away, but I think it's 30.4 volts, and an IMP of 8.22 amps. Okay. Just again, very basic here. The VMP is the voltage that the panel should be producing under standard test conditions. And standard test conditions are 25 degrees Celsius, which is about 77 degrees Fahrenheit, and 1,000 watts per square meter irradiance, and 1.5 atmospheres. We don't really care much about the atmosphere thing. So for this case, we're really only going to look at temperature and irradiance, how much sunlight is hitting that panel. And temperature typically mostly affects voltage, and irradiance mostly affects amperage. Now, it's not 100%. It's not only or exclusively, but for these calculations, close enough that we will factor in temperature when we're calculating voltage. We'll factor in irradiance when we're calculating amperage. And you'll also see there are a few other numbers there. There's the there's the ISC, which is the amperage that panel, the maximum amperage that panel might produce. That's a theoretical measurement. We're worried about actual here, so we're going to deal with VMP and IMP. The ISC we use when we're sizing the wire. That's kind of a worst case scenario, so we utilize that in the design process. The VOC is the theoretical maximum voltage that panel could produce under standard test conditions. Again, we use that in the design process to make sure that our systems do not exceed the threshold that is mandated by code. For instance, for a residential system in the US, it's 600 volts. For a commercial system, might be 1,500. So that's that's why we use those numbers. But for this exercise, we're using actuals. So VMP, IMP. The other number you're going to need to understand is down there underneath temperature coefficient. And temperature coefficients are how much is this thing going to vary per degree Celsius off of standard test conditions. So standard test conditions being 25 degrees. So if it's warmer than 25 degrees, this thing at the Pmax, which is essentially at operational conditions, that's the one we're going to look at, is going to vary 0.45, I think, percent, or about 0.5% per degree Celsius. So if it's 10 degrees warmer than 25 degrees Celsius, 10 degrees Celsius warmer, then that panel is going to produce 4.5% less voltage than it would under standard test conditions. If it's 10 degrees colder, it's going to produce 4.5% more. Okay. Hopefully this is just a quick little review, but for those people who are watching it who don't understand or haven't done this before, that's where we're coming from. Okay. So now that we've got the specifications from the panel, the thing that we need to do is we need to take the temperature of this solar panel. When we're doing the design, we're dealing with theoreticals. So we go, okay, what is the standard test conditions? We know that, 25 degrees. What is the coldest temperature or the hottest temperature ever experienced there? We do that for our string calculations. But for this, we just need to know, what is it? What is it right now? So you use an infrared thermometer and you take the temperature, but you take the temperature of the panel at the back of the panel. Not at the front. You're going to get an overinflated number if you take it from the front. You just want to measure the cell temperature, and it's best to do that at the back of the panel in the shade, but you're still going to see what is that cell temperature. What's the heat of that temperature? You can use one of these little handheld devices, or a couple slides from here, I'll show you another device that you could use for this as well. So you get the real world, actual right now temperature of the solar cell. That's something else you need to get. All right. So then you also want to get what is the actual real world irradiance. Well, you'll need to have an irradiance meter or a solar meter. You'll often hear these, or even a parameter is another term for it. And you want to lay that right on the face of the panel at the proper angle, at the proper orientation. This particular meter there that's pictured is from Fluke, and the little sensor is up near the top, so the guy's hand's not blocking it. And so then you're going to see how many, what is the irradiance? How many watts per square meter is that panel system being subjected to at that moment? All right, so armed with this information, oh, before I get into this, this is another, they do have these kits. This is a Fluke kit here where you can use that irradiance meter, but it also has a connected thermometer that you can just attach to the back of the solar panel, and you can get all of your readings all at once. And in fact, I think this thing even has a data logger, so you could record that. So when you're commissioning your system, and if you need to give a report to somebody, you'll have that you can print out. It will also track the angle, the azimuth of your array. It'll put all of that information in there as well. So a handy little tool, but I mean, if those of you who have bought Fluke tools, you know it's going to be a wee bit pricey. So there are other alternatives. You can get some cheaper meters. You can get one of those handheld irradiant or thermal infrared temperature thermometers, and that's sort of the poor man's way of doing it. All right, so armed with these numbers, well, from our reading in this example, we found that it's 42 degrees Celsius. So the cell temperature is 42 degrees. Well, we know standard test conditions, 25 degrees. So there is a delta or a difference of 17 degrees Celsius. So 17 degrees Celsius times the temperature coefficient at Pmax, which is how much is it going to vary per degree Celsius. So we take 17 times 0.45, and we find that this panel is going to differ or from standard test conditions 7.65%. Well, the temperature is warmer, So then the panel is going to produce less power. So we're going to say, all right, instead of it producing at standard test conditions, we now know it's only going to produce about 92%, 92.35% to be exact, of what the panel is rated for. So we look at the VMP, and the VMP is how many volts is this panel going to produce when it's operating at standard test conditions, times 92.35% or 0.9235. And we find now that that panel is only going to produce about 28 volts. All right, so instead of the 30.04 volts, it's going to produce 28 volts. We did that by adjusting voltage for temperature. Now we're going to adjust amperage for irradiance. So our irradiance meter is in this example saying that there's 934 watts per square meter. Standard test condition says 1,000 watts per square meter. So the math on this is pretty easy. It's just going to be 0.934. All right. So we take our IMP, the amps that it produces under standard test conditions, times 0.934. And we find that given the amount of sunlight that's hitting the panel at that moment, we should be getting about 7.7 amps of production from each of these panels. So we take our 28 volts times our 7.7 amps, because watts equals amps times volts. And we find that this panel, which was rated for 250 watts, should, under these conditions we're experiencing at this moment, produce about 215.6 watts. So that is when it's working as designed perfectly. All right, but there's more than one panel in this system. There are actually 20 panels in this array. We had an array of 20 panels, 250 watts per panel. That's our 5 kW system. So we take 20 times 215.6. We find that the array is now outputting 4,312 watts. Well, if you go and look at the output from the inverter, it's not going to be 4,312 watts, because now we've got to apply the D rate. The D rate factor is basically what are all of the system losses from the output of the panel to the output of the inverter. How much are we losing through this process? Those of you who have gone through my class, you go through that process. You say, okay, first we've got to calculate voltage drop. So voltage drop, we want to keep to less than 2%, ideally. You can never get it to 0. And that's a factor of how big is the wire, how long are the runs. Other issues that will come into play are going to be losses due to connections. Every time you put some sort of switch or disconnect in there, you're going to have a little bit of loss in there. And then, of course, the other major one is going to be how much is lost through the inverter as we're going from DC to AC. Today's inverters, we often find, are only going to lose 2 or 3%, but it's still something you've got to account for. So, for instance, you might have 2.5% from voltage drop and connections. You might have another 3% from your inverter. Then there's, of course, when you're putting strings together, there's going to be mismatch of panels. If it's plus or minus 5%, then when you hook them together in a string, it's always going to produce at the lowest common. So that's going to be minus 5%, which is one of the reasons why optimizers are a good thing, or any of those electronics that get on connected there, is you avoid that loss due to lowest common production value. So there are going to be some other losses. You're going to have to factor that in when you design your system. In this example, we estimated 87% or 13% loss from the DC array to the AC array, or to the AC output. That may be a little bit high in today's market if you're using optimizers or microinverters. When I design a system anymore, I usually plug in 10% just to be safe. Anyway, so we take our 4,312 watts from the array, multiply it times 0.87, and we find that this panel, or this array, should be producing 3,751 watts at that moment. So you go to the inverter output. If it's producing somewhere near there, because of course conditions are going to change a little bit by the time you run back and look at these things. But that if it is producing that, then your system is producing as designed. If it's not, well, now you got to do some troubleshooting. If it's only producing 2,000 watts, something's wrong. Maybe one of the breakers in one of the strings is disconnected, or a wire is loose, or something like that. So that's what you got to do. So that's basically how you're going to design that, or check that your system is matching the output that the system was designed for. It's not going to help you convince the homeowner, if you haven't level set ahead of time that 5,000 watt array is only designed to produce 3750. But maybe what you can do is install it on a sunny February day when it's minus 20 degrees outside, and then you're really going to impress them by how much that thing is producing at that moment. So anybody have any questions from that, or anything else in the world of solar? I'll let you pop in.
Good morning.
Yep. Hey, good morning, Ed.
My name is Ed. I have a question. It's somewhat related to the analysis you just did in terms of power losses and efficiency and such. Maybe I should give you a little bit of my background first so that you know how to answer. Solar power is brand new to me somewhat. I've read through Peter Kevorkian's book, Solar Power and Building Design. I've been through the Sandia Labs standalone PV system paper. I've taken your course on how to design a little standalone PV system, a solar generator. My background, I'm an electrical engineer, but I focused on microelectronics and circuit boards. So I've had the power classes in college. That was a long time ago. My wife and I are developing a property, and it's going to be off-grid solar. It's cost prohibitive to bring grid power to where we're located.
Okay.
And so I'm thinking about well pumps and the power requirements for a well pump, and trying to trade that off with the voltage supply to the pump. I've done some rough calculations. I need about a half horsepower, and that's about 400 watts or so. And if I run that on 120 volts, it's going to require about 3.3 amps. And if I run it at 240, it's going to be 1.6 amps.
Okay.
So smaller cable, less voltage drop, less power loss in the cables. But I'm trying to understand, is it really worth buying an inverter that's going to be have a 240 volt output? And one thing that's really puzzling me is the batteries are rated in amp hours.
Yeah.
But energy is energy and power is power. If I draw less current from the batteries, will the batteries last longer? Will they discharge quicker? There's still the energy piece of it, right?
Yeah.
So how do all those trade-offs work? And
yeah, you've just asked a whole course worth of questions there. Yeah, let me try and touch on some of those, because one thing to consider is that the pump that you're using, I guess you could get a DC pump, which would not require an inverter. But the sense is going to be that you're going to have an AC pump. Well, with your standalone system, the inverters are standalone inverters. So you're not really typically talking about a 240 output, although you can get them, but that would be quite a large inverter for something like that. So you would be looking at an inverter that would either be 120 or typically it's going to be 120 for something that small. So the input is going to be either 12 volt, 24 volt, or 48 volt typically for something this size, because it's not a very big system that you're looking at. The other thing, go ahead.
Sorry. Let me interrupt for just a second, because it might be a valuable piece of information now that you stated that. So this system is also going to run the house. The house won't have any. The house won't have any 240 things in it, but so I'm trying to develop the system that'll run the solar, run the well pump plus the entire house. I did look at the Schneider Electronics inverters that have a 230, but I haven't priced them out yet. So anyway.
Can I ask a question?
Yeah. Hey, Don, you've got a lot of experience in this.
I was going to say, I've got an off-grid house with a well pump that runs on 240, and I'm not an electrician, but when we put it in, my understanding was since it was running the whole house, we ran it into a normal service box, and then I've got a couple of 240 lines, one for the geothermal and one for the pump. I know there's no separate inverter for that. I know my cousin just set it up to run 240 lines the same way at the house here. I've got like an air conditioner heater that runs on 240 and just came out of the panel that way.
Yeah.
Is there any reason you couldn't do that? I mean, I think it would just be a component of the whole system, wouldn't it?
Yeah, I would say yes, that would be a good system if you're running your whole house. I was coming from the place of just running a pump, just a small system only to run the pump. But and you've got like a Solarc, is that the system you've got there? Solarc is something, Ed, that you might want to look at because a lot of folks have had good luck with that.
Solarc.
Solarc, yeah, SOLARK, is that right?
Yeah, SOL-ARK. They're out of Texas, mostly U.S. I mean, U.S. That's their thing. They make it in U.S. and all that.
Yeah. And the other thing is basically in this case, your pump is only just another load that you would factor into your overall system demand. But one thing about pumps, it's a motor, and so the startup amperage, there's going to be a spike, when it starts up. So you often have to design your system a lot bigger, a lot more robust than just the running amperage that you would calculate.
Okay,
So,
yep, that makes sense.
Yeah, so your inverter, give you an example. I have a small solar generator that I wanted to use to run the inline pump from our cistern if the power goes out. And it's rated for like half a horsepower or something like that. Well, it's running rating, if I remember, horsepower is like 700 and some odd watts. So if I did all the calculations, it's not that big of a draw, but you try and hook it up, and the actual spike at the beginning of the process was like 8 times what the rating is when it's running. So the inverter had to be sized pretty robustly to handle that, because it only takes, if you hook up an inverter that's too small for that, it's just going to squeal and shut down, you're not going to operate. So make sure your inverter for your whole house, that's probably not an issue because all of your spiky loads are not going to take place simultaneously, so there should be enough capacity, but it's something you would factor in.
Okay. So you're thinking, go ahead and go with 240 for the pump side, or bring on
Again, it's going to be an economic decision because how big is your house? Is it a one-room cabin? Is it a full home? I mean, there's a lot of things in there, but there's a big advantage as was being pointed out there, as Don was saying, that you can just wire the home traditionally with a standard old service panel, that assumes 240 is coming in from the grid. And then you just simply run everything from single pole breakers as 120 if you don't have any 240 loads. That gives you the other advantage of sometime in the future, you might have access to the grid. You might want to bring in grid service. Well, your house is wired for it, if that becomes a case. So,
okay. And theoretically, does that really, I mean, just maybe this is just academic now, but does the battery discharge rate change at all?
Yes.
At a higher voltage because you're pulling less current out of the battery?
No, the voltage is not going to really matter on that case, because what happens is the battery amp hour rating is based on like a standard test condition of C20, which basically says going from full to empty over a 20-hour period. So for example, if you've got a battery bank that theoretically is rated at 100 amp hours, it's rated at a discharge rate of going that capacity over a 20-hour period. If you discharge faster than that, the capacity will be significantly less than that 100 rating, that 100 amp hour rating. So if you do it at 20 hours, let's say you have this 100 amp hour and your loads drain it over a 20-hour period, you're going to have 100 amp hours, discounting depth of discharge and all these other issues. But if you do it in 1 hour, it might only have a capacity of 40 amp hours. Sort of like the fact that when you drive a car very fast, you get less miles per gallon than if you drive it at a moderate pace. Conversely, if you discharge it much slower, maybe a C100 where you've got the capacity, but you're not draining it down very quickly, you might have significantly more capacity out of that 100 amp hour battery. Might be 200 amp hours. We run into that in troubleshooting where somebody says, okay, we sized this thing. It should have been enough, but it doesn't seem to be enough. Well, it may be that they're draining it very quickly, that they've got large loads that are just putting more on it than we anticipated.
Okay, great. Thank you kindly.
Yeah, Jay, as you know, I have this design on my off-grid cabin, 120 volt. I put my email on the chat. If Ed wants to reach out to me, I'd be happy to give more information about my system.
Okie doke. Yeah, so
Thank
Ed, you
you
can just jump into the chat and write down his email. We won't broadcast your email out there into YouTube Wonderland or anything like that.
Thanks.
So. Right.
Thank you, Gabriel. I got it.
Okay. So anybody else have any questions or any comments before we call it a day? Yeah.
Yep. On a different topic, you might have already seen this, but I saw where there's a webinar tomorrow people might be interested in for the Toledo Solar. They're talking about their cadmium telluride PV modules. I don't know if you saw that. Renview and Toledo Solar are having a webinar for that tomorrow if anybody's interested.
Okay. Yeah. And in fact, there's a nice podcast out there called Factor This that's put on by one of the magazines, Solar World or something like that. Anyway, I heard an interview with the CEO of Toledo Solar, and it's a very fascinating company. And the thin film technology that they're using sounds very interesting. We've always taught that the grading of solar panels, there's monocrystalline, which is the best, polycrystalline, which is sort of medium range, and then thin film is a lower quality. Well, he's making the argument that in many cases now with the new technologies, this thin film technology is as robust as silicon and actually produces better, which is one of the reasons why utilities are using it quite a lot. And they're one of the two manufacturers here in the United States that are truly 100% US manufactured solar panels, not just assembled where they're taking Chinese solar cells and assembling them, because they're a thin film technology. And that's First Solar, which is up in Toledo, and Toledo Solar, because they're both sort of offshoots from the University of Toledo technology. And but the difference is First Solar only sells to utilities, and Toledo Solar is now going out there in the commercial and residential marketplace. So that's something I'd encourage. Don, do you know, I guess people can just Google it. Oh, you said it's through Renview?
It's through Renview. I could send you they send me the stuff. I assume they send it to you too, but
I didn't see that one. Maybe I'm not buying enough product. So
I don't know.
Yeah.
I'll forward it to you, and if anybody wants to know what I can, if they send me something, I can forward it to them.
Okay, so yeah, I don't know. You can put your email in the chat too for people to contact. But if you just Googled Renview, RENVU,
I think if you just do that, you'll get it.
Yeah, and it's they do some really good webinars, and they're free. So I'd encourage you to do that. It's very interesting subject. Also, I got a notice from, and I listened to this week one from the University of Pennsylvania, or maybe it's Pennsylvania State University. They have a webinar system series that they're doing on solar once a month. The first one was on utility scale solar that's taking place in Pennsylvania. So you might want to check out Pennsylvania State or University of Pennsylvania solar webinars. And that's another thing. Or if you send me an email, I think I've got that link somewhere as well. So
No, the extensions, Pennsylvania Extension Service.
oh, it's Pennsylvania. So it's not a specific university?
Oh, no, it's all out of Penn State. I'm sorry. Yeah.
Oh, okay. All right. So the extension service there. Yeah, they seem to have some really good expertise. And I think you, Bruce, had sent that to me. And it was a good webinar. Although I got a phone call in the middle of it from somebody that needed my immediate attention. And so I missed a fair amount, but it was nice they recorded. So if I do have the time, I'll go listen to it. So. All right. Any other questions for the good of the cause?
Yeah, Jay, Devan here again. With respect to, I've been doing some stuff with the agrivoltaics field right now in Trinidad, right? Some projects. And I've been doing some little studies on the type of PV modules used in those type of applications, as well as the construction of the ground mount and racking. A lot of that has to do with control of the amount of light going through the being allowed onto the ground. And I think notice a mention of research being, or production being made on transparent solar panels, where you can actually control the amount of light, as well as there seems to be PV modules which are manufactured with a thin, long profile, if you understand what I'm saying.
Yeah.
So I don't know if you have any more information about, I'm trying to reach out to anybody who might be in that business in terms of the supply of PV modules. Anybody can also reach out and make a contact for me.
Okay, yeah, I think we've seen the interest in transparent or translucent solar modules, not only for building integrated systems where you want to use them as windows, but for agrivoltaics where you want sunlight to penetrate through for some crop production underneath the solar modules. I know that the perovskite is the technology that is promising translucent or transparent modules, but that's still not in commercial production to my knowledge yet. They are using perovskite as a layer on some solar silicon panels. But I have seen some panels where the gap between the cells is clear glass, which does allow for sunlight to penetrate through, where it's not transparent cells per se, but there's a number of transparent parts of the panel itself. So you might want to look at that and see if that's going to meet the needs of what you're looking at. But I suspect that's going to be a little bit pricey, for those kind of panels. So does anybody else have anything for Devon and down there in Trinidad where you got to maintain paradise as you're putting up solar panels, right? So, all right. Any other questions then? Okay, well, then we'll call it a day. We'll see you guys all next week. All right. Take care. Bye-bye.
Thanks, Jay.
Sure.
Thanks, Dave. Bye.